automated driving, autonomous vehicles, connected cars. And so I'm pleased that we have Dr. Guarav Bansal here. Tell us a little bit about what's happening. So Dr. Bansal received his bachelor's from IIT Kanpur, his PhD from, I think it was University of British Columbia, and then has been a frequent attendee of various standard bodies related to the development of DSRC, and also given a number of tutorials on DSRC, which is a key technology in the automotive space at many of the conferences we attend, like at ICC and GloveCom. So, Guarav, please come up here and tell us your views here on the role of the vehicle in 5G.
Thanks, Robert, for the introduction. My name is Guarav Bansal, and today the title of my talk is Potential Applications of 5G Communications in Automated Driving. So first, I'll talk about connected car and how connected car can enable reduced crashes and what automotive industry has done about it. And then, because this workshop is about 5G, I'll specifically talk about automated driving and intelligent intersections and how 5G can play a big role in realizing these two things. And in the end, I'll conclude my talk. So there are some numbers on how many crashes happen just in US alone. In US, every year, there are 37,000 fatal crashes. That means more than 100 people die every day in car accidents, just in US alone. There are more than 1.7 million injury crashes per year and 4 million plus property damage crashes. So we have more than 6 million crashes that happens just in the United States, and we have similar numbers in Europe, Asia, and everywhere else. And interestingly, 40% of these crashes happen at intersections. And we believe as Toyota and as automotive industry that if car would be connected to other cars, to infrastructure, to cloud, using low latency, high bandwidth communication, we can reduce these crashes. So how do we achieve this? We have built a technology where if cars are transmitting something very simple as beacon messages, where every car is equipped with a GPS and a radio, and it's transmitting its location, its speed, its heading, every certain times per second. And here in this figure on the top right corner, you see an intersection warning. What can happen is if two cars are approaching the intersection, and they're transmitting these messages to each other. And a very simple algorithm can be written on the car, which can detect that if the driver is not stopping as the car is approaching the intersection, then a warning should be given to the driver that if it won't stop, it's going to run into another car. So another question that comes up is, can we do it this kind of accident prevention using onboard sensors like radars? But what is the main difference between radar and communication is that using radar, we can only estimate the speed and the location of the car in front of us. But using communication, we can actually share information among the cars, and we can share more accurate vehicle state. We can do it in a frequent broadcast 360-degree dissemination fashion. And it provides us some of the important capabilities like long range. You can communicate with non-nearest neighbors. You can communicate with non-line of sight neighbors. And so now what have we done about it? So for many years, like more than 10 years, auto industry has been working on this technology called as DSRC, which stands for Dedicated Short Range Communications. It's an ad hoc networking technology which gives us this low latency and allows cars to communicate with other cars, with roadside devices, pedestrian bicycles. And it has been standardized. The IEEE portions are very similar to like the ones in Wi-Fi. The standard is called 802.11p. And this technology is moving very close to deployment. And there are different deployment models that are followed in various countries. Like in US, we are going for a mandate. It's expected that the next year, sometimes next year, government will mandate DSRC, which will require every car OEM selling car in US to have the car equipped with DSRC. In Europe, all the major car makers have signed a memorandum of understanding, which would require them to start deploying DSRC at a certain date. But in Japan, what's happening is Toyota has more than 50% of the market, and they have decided to deploy DSRC on their own. Just 2 weeks ago, we announced that we are bringing DSRC to mass market models in Japan. And the reason why this kind of either memorandum of understanding or mandate or like having a large volume is required, because you get low benefits when the penetration is low. So if everyone kind of does it together, that's when you will realize the maximum benefit. So without going into too much details, the message set for DSRC has been standardized in SAE, and in this message set, every car basically transmits its location, its speed, its heading, and some of the information that it gets from the onboard sensor like acceleration, brake status. And as far as the spectrum is concerned, in United States, 75 megahertz is allocated for licensed DSRC use, and it's free to use for this purpose, out of which 5 megahertz is a guard band, and then there are 7 channels of 10 megahertz each. So these applications that I'm talking about here, they're all in channel 172, which is the safety channel for DSRC use. And these are some of the applications that are designed by the auto industry. I touched on the intersection application earlier. Similarly, there is an emergency electronic brake light application, like if a car is stopped because of brake failure, then it can start transmitting this message, and the cars who are coming close to this stopped vehicle would know about it and can warn the driver. And not just the V2V safety application, there are lots of other applications that are designed by the automotive industry. This is taken from the US DOT website, that similarly you can design a V2I application where if you are violating a red light, then the warning can be given to a driver. And similarly, the applications are designed to make cars more fuel efficient, make it a better driving experience. One of the applications I can highlight here is cooperative adaptive cruise control. So this is like an adaptive cruise control, but the car that you are following, you are able to exchange messages with it. And when you do it, the driving experience that you get is much more smoother. And in Japan, when Toyota is deploying DSRC, they are doing it along with the also deploying the CSCC application. So now here, like the motivation of my talk here is to talk about the applications where 5G can play a role in the connected car. So far the things that I've covered is where the human is in control, and these the messages that would be exchanged would be primarily used to give warning to the human driver. But there is another parallel, very important thing that's happening in the automotive industry, and which is going to revolutionize the whole industry, is self-driving car. A self-driving car would be capable of sensing the environment and driving on its own. So because in our research group, we have been working in DSRC or in V2X for a long time. So now we are looking into how can we design the V2X communication for automated car. As many of you might have seen the ads about or the publicity about the Google car, and also the automated car from many other OEMs. So most of these cars use onboard sensors like lasers, radars, and camera. But we believe that V2X communication is also going to play a very important role in self-driving car, because it can provide these 3 unique capabilities of long-range sensing, non-line of sight capability, and collaborated driving. And here I present a very like a practical and a very simple use case that how communication is going to be important. For example, an automated car is approaching on an intersection, but there is a child running from a perpendicular street. There is no way that by using your local onboard sensors you can detect that child. The way you can get the information about this child is that either a roadside device sees this child through its camera or through its lasers, or an automated car on the same side of the street sees this child and then transmits this information using a low latency, high bandwidth communication to the car approaching. Similarly, there might be some construction going on the opposite side of the street, and if a car is approaching which cannot see the construction, that information can be relayed. So now what is the main difference between what we were doing for DSRC safety communications and what would be required for automated car? So what we were doing so far for DSRC safety communications, when human is in control, we are just transmitting the information of our own car and the information of our GPS, like where the car is, where it's going. But in the automated car, what would be required is we not only transmit the information of our own car, but also what we are seeing on the road, other cars, other objects, other pedestrians. So keeping this in mind, we have proposed a system model that an automated car application will run on a real-time map, which would be built in collaboration with the local sensors and the communication module. So here I'll present some results to show which kind of motivates that why the current DSRC technology that we have is not sufficient for automated driving. And one point that I would highlight is there is also kind of, when we are designing this automated driving communication, one debate is whether to transmit the raw sensor information or the process sensor information. Some people think that it could actually be useful to transmit raw information, and the reason is that my Lexus in 2017 might not have the same sensors as my Lexus in 2020, or my Corolla might not have the same sensors as my Lexus. So if I transmit a raw information, then the Lexus or the Corolla, whoever gets that information, they can use their own detection algorithm to derive whatever information that might be important to it. But of course, keeping the realities in mind for the current day communications, especially DSRC, transmitting raw information is not possible. So the results here I'll show is actually for the processed information. Like in the slide that I showed earlier, we're not going to transmit like an image of a child. We're just going to process that and represent it through, we did some studies and we found out that we can represent an object roughly by 50 bytes. So the simulation results that here I'm going to show, we configured a network simulator where we set up a road 4 kilometer long. We set up the car density to be 100 cars per kilometer, which by the way is not a very high density. And we were transmitting the message, which has the range of 500 meter, and we were transmitting a message every 100 milliseconds. So we know with our work in DSRC, that including the security overhead, the message size is typically 350 bytes. But now when we're trying to do automated driving, our message size would be 350 plus X into 50 bytes, where X is how many objects you are trying to transmit. So here there are some results for CBP, which stands for channel busy percentage. It's a measure of how busy your wireless channel is. So on the y-axis here in both the plots, we have plotted the CBP, and the x-axis is just the simulation time. And on the left-hand side, we are plotting the CBP numbers for the 7 random cars picked on this 4 kilometer long topology. And what you see is that for DSRC communications, your CBP is somewhere around 60 to 70%. And because DSRC uses CSMA, CA-based MAC, when your CBP is between 60 to 70%, that's when you get the highest throughput. So our channel is working fine. But when we try to do the same for automated driving, where here we have assumed the X to be 40, that means every car is transmitting the information about 40 other objects. The packet size becomes 2350 and the CBP becomes very high, close to 100%. That means channel gets saturated and your packet error ratio is going to be very high, almost 100%, and the wireless channel is broken. And actually the results here are not surprising at all. This is not magic, because DSRC right now uses the PHY and MAC, which is based on a almost 10 years old standard. The highest data rate that we can get is 6 Mbps. And now when we want to transmit this high packet size, even for the processed information, the current day DSRC cannot support it. So there can be 2 ways how this kind of the application requirement can be supported. One would be that we develop a DSRC version 2 with a new PHY, new MAC, and also innovative algorithms would be required that we are not flooding the wireless channel by sending redundant information. But I also see that here there is an opportunity for 5G to create a low latency, and by low latency we mean less than 10 millisecond delay and high data rate, higher than 1 gigabps, which can support more than 250 million cars in United States, and similarly in Europe, Japan, everywhere else, to support the automated car, where we can share the raw sensor data or process sensor data between the cars. We can talk to the roadside devices if they have the sensors. We can talk to the pedestrians. There has been work done where this kind of a chip can also be in the smartphone, so when the pedestrians are on the road, they can transmit and receive messages from automated car. And similarly, there can be applications where automated car can communicate with when I'm filling my gas or when I'm going through a drive-through. Maybe I don't need to use a credit card anymore while I'm making these payments. They can be done over the wireless channel. And another important application for 5G that I want to highlight here is related to cloud. So what's going to happen in automated driving is, one of the important thing is they would require high definition map. And by high definition map, I don't mean this, the Google map or Bing map that we used every day. These would be the maps which would clearly show where the lane is turning, where the lane markers are, because such kind of very accurate precision would be required for the steering, and such that the driving experience is very smooth for the passenger sitting in an automated car. And we estimate with some of the studies that we have done that let's say if I'm living in Bay Area or I'm living here in Austin and I buy an automated car here. So I'll maybe when I'll buy the car, it'll come preloaded with the high definition maps for my area. And every day some changes would happen. Maybe there are some construction that comes up. So that those maps would be downloaded to my car. And they might be somewhere around 1 to 2 gigabytes. But what can happen is, let's say one morning I wake up and now I want to go to Houston. And now my car needs to download the map from the way from Austin to Houston. And that might easily be tens of gigabytes of data. So if 5G can allow us to be able to download this data, and especially I think what's very important is if it can be done in a low-cost fashion. And another important thing here is to upload the data to cloud. So as many of you might have heard that Tesla yesterday, they started deploying some of the automated driving features in their car. And one of the things that they're trying to do is they're trying to upload the sensor data that like around 100,000 cars that they have to their server, because when all the sensor data that these cars are measuring, when it goes to the server, they run machine learning algorithms because car has acted in a certain way on the basis of a certain sensed information. But you can train your machine learning algorithms on the basis of that, and then you can download the new automated driving software to the car. So while we're designing automated driving, it will be very important that we can upload the raw sensor information, raw or process sensor information up to the cloud. And that would, again, can be tens of gigabytes of data every day. So now I'm also running out of time, but just very quickly I'll motivate one more application that when the cars would be automated, can we do something about the traffic? Like that's one of the biggest problem in America. Like I live in Bay Area, we have the worst traffic. The traffic moves very slowly. And there has been recent work done in CMU, here in UT Austin, and in Virginia Tech, where they have showed that if we can design like smarter traffic lights, we can improve the traffic by almost 35% for urban commuters. These were some experiments done by CMU in Pittsburgh and also in Portugal. And for the rush hour, we can reduce the commute by 40 to 60%. So I'll just, assuming if I can start this video, no. So I had a video and I don't know how to start it, but I think that's fine. This is from the work done here by, actually in computer science department by Professor Peter Stone. It's a very similar idea on how a future intersection can look like. And to enable this kind of intersection would again require low latency communication between the roadside device and the car. So just in the end, to conclude my talk, we believe that V2X communication will play an important role in enabling reduced crashes. DSRC is moving close to deployment in many parts in the world, but also at the same time, high bandwidth, low latency communication is required for automated driving applications, specifically to enable non-line of sight view, long range sensing, collaborated driving, downloading high definition map, and it can also help in enabling intelligent intersections, which can give us high throughput and reduce crashes. So, thank you.
Time for a couple questions. The frequency band of DSRC in Japan, what is it, and is that globally standardized, or is there activity to do that?
So that's a good question. In Japan, we have there's a 10 megahertz channel in 760 megahertz frequency. And I don't think that we'll get the same band in US or Europe, but automotive industry was lucky in Japan to get that band because it's a lower frequency. You get a better propagation in it. So right now when Toyota is deploying in Japan, they're deploying in 760 megahertz. But there are no like ongoing efforts to get the same band in US or Europe.
Yeah, I have a question that what you do with the legacy cars, like I have a 1970 Buick.
Yeah.
So it doesn't have, you see, all
Yeah. Yeah, what's hopefully going to happen is you can buy an aftermarket device. You can go to a dealership and you can buy an aftermarket device for $200, $300, which can be installed in your car, and you can again, like at least be able to transmit DSRC messages, and maybe hopefully some kind of interface can be designed in that kind of aftermarket device that can also give you a warning when you buy it.
Yes, I think one of the major challenges they're facing with driverless car, and they're sending the sensor information in real time to the cloud, is that they are losing the reaction and control in real time because they're losing in terms of delay going to the cloud and coming back. And there are some discussions of bringing such a cloud at the edge of the network closer to the sensors. What's your views on that?
So in my talk, I'm talking about two kinds of communications. One is like real-time communication where we require this less than 10 millisecond latency, and which is kind of what DSRC does today for human-driven cars. So we would require that kind of communication, for supporting, especially sharing sensor data for real-time use case. But as you are correctly pointing out, there would be other sets of application for which we will also require cloud. Like specifically if there are applications where my automated car can wait few seconds, before acting on it. So few second delay can be handled by cloud. And this example that I pointed out about high definition map, that's something a cloud-based application which can, you can have few seconds or even like minutes of delay in enabling that. So we would require both kind of low latency V2X and like relatively high latency cloud communication.
All right, we got to move on here. Guarav, thank you here. All right, I've done a horrible job of keeping the program on time, so fortunately we have about 3 minutes left for the next